Hi everyone, today we are presenting our work, Robot Learning on the Job, Human-in-the-Loop Autonomy and Learning During Deployment. We have seen significant development of robot learning methods in recent years, achieving impressive results in research settings. However, robots today still fall short of generalization and robustness for robust deployment in the wild. How can we reliably deploy learning-enabled robots to real-world tasks? The conventional robot learning paradigm is to train a model and then deploy it. And once the model is deployed, we can only hope for the best. The model cannot handle unpredicted failures and lacks performance guarantees. To ensure safe and reliable deployment, shared autonomy methods propose to make decisions from human robot teams. But they don't seek to improve the robot's performance over time, and the human often has a high workload when working with the robot. Interactive imitation learning aims to improve the robot's performance with human feedback. While promising, existing methods require a large amount of human supervision and cannot scale to long-term deployments. Our key idea is to improve robot autonomy over long-term deployments with human in the loop. We present the series framework where a robot learns on the job. In this framework, a human and a robot collaborate through shared control. Data from deployments will go into the memory storage and will be used by our algorithm to improve the robot's policy. Series learns and deploys continually, improving policies from human feedback and robot deployment data. Deployment data is passed to policy training, while a newly trained policy is deployed to the task environment. The two threads of model update and deployment run in parallel. As time goes by, the robot improves its autonomy and human workload is reduced. Next, we illustrate how human-robot teaming ensures trustworthy deployment. A robot executes the policy for the task, while a human monitors the robot execution. At the beginning, the robot performs the task, while the human monitors. After a while, the robot gets stuck at inserting the gear. The human now decides to intervene and takes over control, and the robot can then proceed to do the rest of the task autonomously. Our problem setup presents unique learning challenges. First, how can we learn from the deployment data that comes from both the human and the robot? Our insight is that human interventions can tell us when the robot will fail and how to recover from failures. Take this as an example. The robot tries to grasp the gear and fails, and the human intervenes. We note that the states before human intervention are abnormal states that should be avoided, and the human intervention are valuable corrective examples to learn from. We introduce an intervention-guided imitation learning algorithm where we assign higher weights to human interventions and lower weights to abnormal states before intervention. This allows us to leverage the inherent structure of human-robot team data for policy training. A second challenge is how to handle a growing memory size as deployment continues. The key idea is to prioritize important training samples and discard less useful ones. We first filter the trajectories according to a memory management strategy. For example, keeping the most frequent intervene trajectories. We then reduce the dataset to a fixed size. By learning on this reduced dataset, we enable greater sample efficiency while achieving high performance. We evaluate the robot policy performance on 4 tasks: nut assembly, two-hand, gear insertion, and coffee pod packing. Our autonomous policy outperforms baselines consistently over 3 rounds of training and deployment. As the robot policy improves over time, the amount of human workload decreases. We visualize the human intervention distribution of gear insertion for round 1 and round 3. We see that for round 1 deployment, there are frequent human interventions. But at round 3, the robot runs autonomously most of the time. We show how series learns more effective policy compared with baselines. We specifically compare it to IWR, the state-of-the-art interactive imitation learning algorithm. For the gear insertion task, IWR fails to overcome bottleneck states, while Cirrus has better precision and self-adjustment. In summary, we presented Cirrus, a trustworthy robot learning framework that improves robot autonomy over long-term deployment. Cirrus uses intervention-guided imitation learning and memory management strategies for continual policy learning. One limitation of our work is that it currently needs constant human monitoring and trains policies from scratch for each update. Future work can study developing error detection mechanisms and improving learning update efficiency. Please visit our webpage for additional details. Thank you.